Hello viewers, in today's class we are going to discuss an important definite integral involving greatest integer function, right? So let us solve this definite integral from minus e to e and greatest integer x square minus 1 dx, right? And here e is the exponential number, right? So let us call this integral as I, right? Now let us take f of x is equal to greatest integer x square minus 1, right? And here we see that if we replace x by minus x, then we have f of minus x is equal to greatest integer minus x square minus 1, and this is simply x square minus 1, right? So here minus x square is equal to x square, and from 1 and 2 we see that f of x is equal to f of minus x, which implies that f of x is an even function, right? Okay, so once we have established that f of x is an even function, we can make use of the important property from definite integrals, which says that the integral from minus a to a f of x dx is equal to 2 times integral from 0 to a f of x dx whenever f of x is an even function, right? Okay, so now if we apply this property to this function, because this function is an even function, so we can write this integral as I is equal to 2 times integral from 0 to e and greatest integer x square minus 1, right? Okay, so now our aim is to evaluate this integral. So now what we can do here, we can make use of the substitution method for evaluating integrals. So let us substitute t is equal to x square minus 1, right? So dt is equal to 2x dx, and from here we can write x is equal to square root of t plus 1, right? Okay, and here we have 2 times the value of x can be taken from here, so we have 2 times of square root of t plus 1 dx, and dx can be written as dt over 2 times of square root of t plus 1, right? Okay, so now we can express this integral I in terms of this new variable t. So now we can write 2 times the integral from 0 to e. So now we can also change the limits accordingly. So when x is equal to 0, then we see that the value of t is 0 square minus 1, so this is minus 1, and when x is equal to e, then we have t is equal to e square minus 1, right? So now this integral can be expressed as from t is equal to minus 1 to t is equal to e square minus 1, and here we have greatest integer t, and for dx we can write dt over 2 times square root of t plus 1. So now here 2 and 2 get cancelled, so we are left with I is equal to from minus 1 to e square minus 1, and here we have greatest integer t divided by square root of t plus 1 dt, right? So now here we see that e is exponential number, and the approximate value of e is 2.718, and here we wish to find the value of e square minus 1, which is the upper limit. So e square minus 1 is approximately equal to 6.387, right? So we can take this value as approximately 6.4. So now viewers, if we draw a number line here, and suppose here we have minus 1, which is the lower limit, and e square minus 1 is here, then e square minus 1 is approximately equal to say 6.387, and between minus 1 and e square minus 1 we have the integers 0, then we have 1, then we have 2, then we have 3, then we have 4, then we have 5, and then we have here 6. So it means here we have 7, right? And e square minus 1, it lies between 6 and 7, right? So it lies between 6 and 7. So now from this number line we conclude that this integral from minus 1 to e square minus 1 can be divided, or it can be split between these integrals, that is from minus 1 to 0, then we have 0 to 1, then we have 1 to 2, then we have 2 to 3, then we have 3 to 4, and then we have 4 to 5, and then we have from 5 to 6, and then we have from 6 to 6.387, which is equal to e square minus 1, right? So it means here we have divided, or we have split this integral I into 1, 2, 3, 4, 5, 6, 7 and 8 integrals, right? And in place of integrand we will have this function, right? So now if we denote this integrand by the function f of t, then we have f of t is equal to greatest integer t over square root of t plus 1. Then here we'll have ft of dt. Here also we have ft of dt. So we have these 8 integrals, right? 1, 2, 3, 4, 5, 6, 7 and 8. So now let us evaluate these 8 integrals, and the sum of these 8 integrals would be the value of our given integral I. So viewers, here we have written the value of t in the form of these 8 intervals 1, 2, 3, 4, 5, 6, 7, 8. That is when t lies between minus 1 and 0. Similarly, when t lies between 0 and 1, and so on. And finally, when t lies between 6 and e square minus 1. So by the definition of greatest integer function, when the value of t lies between minus 1 and 0, then the value of greatest integer t is equal to minus 1, and when t lies between 0 and 1, then the value of greatest integer t is 0, and similarly we can assign the value of greatest integer t in these rest of the intervals. So here we'll have 1, then we'll have 2, here we'll have 3, here we'll have 4, then here we'll have 5, and here we'll have 6, right? So let us now evaluate these 8 integrals. So now here let us denote these 8 integrals by I1, I2, I3, I4, I5, I6, I7 and I8. So the value of this integral I is the sum of all these 8 integrals, right? So let us solve these integrals one by one. So viewers, let us take the first integral I1, which is from -1 to 0 f of t dt, and f of t is greatest integer t over square root of t plus 1, and when t lies between -1 and 0, the value of greatest integer t is -1. So here we'll have the value of greatest integer t as -1. So we'll have -1 over square root of t plus 1 dt. So we can take this negative outside. So we'll have the integral from -1 to 0, and this is t plus 1 raised to minus half dt, right? Now here to evaluate this integral, let us find out the indefinite integral of t plus 1 raised to minus half dt, right? So here we'll make use of the substitution method. So let us substitute y is equal to t plus 1. So dy is equal to dt, and this integral now reduces to y raised to minus half dy, and that is equal to y raised to minus half plus 1 over minus half plus 1. So here we'll have y raised to half divided by half, that is equal to 2 times square root of y, right? So the indefinite integral of t plus 1 raised to minus half dt is equal to 2 times of square root of t plus 1, right? Again substituting the value of y as t plus 1, right? So viewers will use this result as the standard result for evaluating the other integrals, that is I2, I3, I4, I5, I6, I7 and I8, right? So now this integral can be written as minus, and the indefinite integral of this t plus 1 raised to minus half dt is equal to 2 times of square root of t plus 1, and now we'll simply substitute the limits, that is from -1 to 0, right? So now here we can take 2 outside, so here we have -2, and first we will substitute the value of t as 0. So here we'll have 0 square root of 0 plus 1 minus, and if we substitute -1 here, so we'll have 0. So here we'll have 0. So this is -2 times square root of 1 is 1. So here we'll have 1 minus 0. So this is equal to -2, right? So therefore the value of I1 is equal to -2. Now let us find out the other integrals. So now let us find out the value of I2. So here I2 is from 0 to 1, greatest integer t over square root of t plus 1 dt. So now here I2 is simply equal to from 0 to 1, and when t lies between 0 and 1, then the greatest integer t is 0. So here the value of greatest integer t is 0. So the overall integrand is equal to 0. So the value of I2 is equal to 0. Now I3 is equal to from integral from 1 to 2 ft dt, and here we see that when t lies between 1 and 2, the value of greatest integer t is equal to 1, right? So here we'll have 1, and we have 1 over square root of t plus 1 dt, and by making use of this integral, we'll have here 2 times of square root of t plus 1, and the limits are from 1 to 2, and if we substitute 2, then we'll have 2 plus 1 3. So here we'll have square root of 3, and when we'll substitute t is equal to 1, then here we'll have 1 plus 1 2. So the value of I3 is 2 times root 3 minus 2 root 2. So now let us calculate the value of I4. So I4 is from 2 to 3 ft dt, and here we'll have the value of f of t, and when t lies between 2 and 3, the value of greatest integer t is 2. So here we'll have 2, and here we'll have square root of t plus 1 dt, right? Now taking 2 outside, the integral of t plus 1 raised to minus half dt. So again, making use of this result, we'll have here 2, and then we'll have 2 times the square root of t plus 1, and the limits are from 2 to 3. Now taking this 2 outside, so here we'll have 4, and then we'll substitute the limits. So here we'll have square root of 4 minus square root of 2 plus 1 is 3, and square root of 4 is 2, and this is 2 minus square root of 3. So this is 4 to the 8 minus 4 times square root of 3, right? So the value of I4 is 8 minus 4 times square root of 3. So now the value of I5 is from 3 to 4 f of t dt, and here when t lies between 3 and 4, the value of greatest integer t is 3. So here we'll have 3. So now this is taking 3 outside. So we have integral from 3 to 4 t plus 1 raised to minus half dt, and here we'll have 3, and again using this integral, so here we have 2 times the square root of t plus 1. The limits are from 3 to 4, and taking this 2 outside, so we'll have 6 here, and square root of t plus 1, and the limits are from 3 to 4, and substituting the limits, so here we'll have 4 plus 1 5. So here we'll have square root of 5 minus 3 plus 1 is 4, square root of 4. So now this can be written as 6 times the square root of 5 minus 2, square root of 4 is 2. So this can be written as 6 root 5 minus 12, right? So the value of I5 is 6 times root 5 minus 12. Now let us find out the value of I6, which is from 4 to 5 f of t dt. Substituting the value of f of t here, and when t lies between 4 and 5, the value of greatest integer t is 4. So here we'll have 4, taking 4 outside. Now we'll have this integral, and again by making use of this result, the integral of t plus 1 raised to minus half is 2 times the square root of t plus 1, and the limits are from 4 to 5, and this is taking this 2 outside, so we'll have here 8, and substituting the value of the limits here, we'll have 8 times 5 plus 1 is 6, so here we'll have 6, and here 4 plus 1 is 5, so here we'll have root 5, right? So now this can be written as 8 times root 6 minus 8 times square root of 5. Let us find out the value of I7. So I7 is from 5 to 6 f of t dt, and now when t lies between 5 and 6, the value of greatest integer t is 5. So now taking 5 outside, then we'll have the integral from 5 to 6 t plus 1 raised to minus half dt, and again using this result, so here we'll have 5, and we'll have 2 times square root of t plus 1, and the limits are from 5 to 6, and taking this 2 outside, so here we'll have 10, and substituting the value of t, that is 6, so 6 plus 1 7, and here we'll have 5 plus 1 6, so here we'll have square root of 6, right? So the value of I7 is equal to 10 times square root of 7 minus 10 times square root of 6. So viewers, let us find out the value of the last integral, that is I8. So I8 is from 6 to e square minus 1, and here we see that when t lies between 6 and e square minus 1, where e square minus 1 is equal to approximately equal to 6.387. So when t lies between 6 and e square minus 1, the greatest integer t is equal to 6 here, and taking 6 outside, we'll have this integral. Now making use of this standard result, so here we'll have 2 times of square root of t plus 1, and here we have the limits from 6 to e square minus 1, so taking this 2 outside, so here we'll have 12, and here we have square root of t plus 1, limits are from 6 to e square minus 1, and let us substitute the values here. So when t is e square minus 1, so here we'll have square root of e square, because minus 1 and plus 1 get cancelled, so we are left with the square root of e square, and minus square root of here we'll have t is equal to 6, so 6 plus 1 7, so here we'll have a square root of 7, right? So we can now write it as 12 times e. Square root of e square is e, where e is the exponential number, and here we have a square root of 7, and this is 12 times e minus 12 times square root of 7. So viewers, once we have evaluated all these integrals, the value of the given integral is the sum of all these 8 integrals. So here we have substituted the values of all these 8 integrals, right? Now we can simplify this expression to get the value of the given integral by simplifying the like terms, right? So now viewers, if we simplify this expression, we'll arrive at this result. So here minus 2 plus 8 and minus 12 gives us minus 6. Then here we'll have minus 2 root 2, then 2 root 3 minus 4 root 3 is minus 2 root 3, and 6 root 5 minus 8 root 5 is minus 2 root 5, and then 8 root 6 minus 10 root 6 is minus 2 root 6, and then 10 root 7 minus 12 root 7 is minus 2 root 7, and then we'll have this term 12e, right? So this is the final expression for this integral. So this is the required integral of this function.